Welcome, everyone. Our first speaker is Norbert Schappacher of the University of Strasbourg. He's probably known to you for a book he published in 2002 called Framing Global Mathematics, which is a history of the International Mathematical Union. He works in number theory and algebraic geometry in his mathematical research, and his presentation today will be related to that rather than the International Mathematical Union. And the title of his presentation is The Long Way to Intersection Theory, like a long way to Tipperary, but the long way to intersection theory, mathematical politics about space curves from Max Noether to the 1990s. Norbert?
Thank you very much, Craig, and thanks to the organizers for having me at this conference, and thank you for even putting me in the first place at this for the first talk. So you notice that there is intersection theory in the title. There's also the word politics, and as you will see during the talk, this will actually be justified that I talk about politics. But since we're at the Newton Institute, I think I should start with a quote by Newton. Curvarum usus in geometria est ut periarum intersectionis problemata solvantur. So the usage of curves in geometry is that by intersecting them, you can solve problems, or you should solve solvantur. You should solve problems. And this is a quote which I found for the first time in this report by Brill and Noether. So here is the title page of this report, and it happens that this report is one of the projects that was actually present here during this activity in modern history of mathematics, because Karine Chemla a few years ago started this. What was it? Is there? Oh, there's a microphone. Okay, all right. Can one sort of turn this down? Or where is the mic physically? I'm sort of confused here. It's just much too strong. I don't know. Is the guy there who? Okay, I just carry on and try to speak. That's a good point. Okay, is it better now? No, it's not, but well, I'll just carry on because I don't have much time. So this report is being translated into English in various translation sessions. It's a big group of people, and most of you know about this enormous project, and there are lots of discussions that we have. So first of all, where to situate this report into, if you want, politics of colleagues and international cooperation in mathematics at the time. So this was a big program. This is really very annoying. Could the technician do something about this? I've given talks here before. See, when I speak, we have an echo. Can you sort of avoid this? Turn it down. So the German Math Society was finally, later than the French one, founded in 1891, and then very soon they had the idea of asking colleagues to make reports, to take stock of what was actually happening in mathematics. And so this is from a later report in 1904, a certain number of reports, and of course you recognize Hilbert's Zahlbericht on theory of algebraic number fields, but there are many others on Fachwerke, and so on. So all kinds of subjects, and there are also other reports that were never written. For example, it was not only Hilbert who was supposed to write a report on algebraic number fields, but also Minkowski about the rest of number theory, and he did work on it for a few months, but then the report never got written. So this is a big undertaking, and it also means that the German Math Society was particularly proud of taking stock of what actually happened. So now, turning to the report that we are translating, and where there are lots of debates about how to translate not only complete, very long, complicated sentences, but also make notes, historical notes about this. It is sometimes interesting to read their own introduction. If the process of our studies, we have become convinced that the history of recent mathematics that wants to go into the inner coherencies has to be split up into histories of individual disciplines, each of which, however, have to cover more than just short time spans. If this conviction is accepted in wider circles, we shall find successors who will carry on the work we have begun by individual studies with the domain we have outlined, or by working on neighboring domains, stressing the threads which connect different periods and scientific disciplines. They will contribute, as we all want to do, to strengthening the idea of unity of science, providing the knowledge for current research of what has already been accomplished, and preserving the image of important men. There are a lot of touchy points. This is a very conscious, very explicit comment on this by Brill and Noether, because parts of the report of the more recent theories essentially describe work by Brill and Noether, or by one of them alone. And they say, okay, so we are a party in this whole game of doing the theory of algebraic functions, but on the other hand, parties do play an important role, so they also have to be reflected. We will be criticized for doing it the way we did, but we do. When we translate this, we note every once in a while comments on other colleagues, in particular Cayley, for example, who is not always commented on very favorably by Brill and Noether. Another problem is, in particular, with writing this report in the early 1890s about algebraic functions, algebraic geometry, as we would say today, is that the field is moving extremely quickly, and so they do say, well, while we were finishing our report, there were other things coming out by Segre Castelnuovo, also by Bertini, and so if it hadn't been so late, we would of course have integrated them into our report. And there is yet another problem, namely certain colleagues who sort of try to occupy a certain disciplinary domain. They were supposed to be present and actually co-active in writing this report, namely Kronecker through a preferred student of his. I think it was Hensel, although it may have been Molk. But then he died, and so this whole thing was not integrated into the arithmetic theory of algebraic functions, was not in the report of Brill Noether. It had to be substituted in 1919 by Emmy Noether, the daughter of Max Noether. Okay, so I just, before getting into my story, my precise story that I want to tell you, make a few remarks that also are things reflected very well in the report, but I'm not going to go into detail. So the first thing, so this is a general list of scattered landmarks of algebraic geometry in Germany at the time, but I will concentrate on something that Max Noether has to do with, namely, first of all, the Fundamentalsatz. What is the Fundamentalsatz? The Fundamentalsatz addresses the question when you have, for example, for plane curves in this case, in this paper, when the fact that f vanishes on the total intersection of two curves, given by phi and psi equal to 0, these are the equations, when is f, as we would say, part of the ideal generated by phi and psi in the polynomial ring. And of course, in general, you have to have some conditions, for example, that there are no multiple points on this. So there's this article from 1873. Then there is Kronecker. This is a nice picture which I like very much, but it doesn't show him at the time when he was giving this lecture course on elimination theory, one of his standard lecture courses that he taught regularly in Berlin. So this is a course from 1885. The problem of general theory of elimination is briefly described there, and then he comes to what he calls the Hauptsatz, fundamental theorem. If an entire function of xy vanishes for all systems of values psi eta, which at the same time satisfies two equations, phi and psi, then it is congruent to 0 for the modular system, phi and psi. And literally speaking, this is not true, but there is a comment on the context, the general context that this theorem has to be viewed in, namely, essentially, he talks about content of equations, and he excludes the question of multiple points. Yet, this was a treatment that even his own students, for example, Jules Molck and Netto, forgot the first name of Netto, I'm sorry for that, did not accept as this, so later on they published papers on this, making things much more explicit and also addressing the general case. And then in Netto you will see that if a certain function gray capital F is passing through the things defined by what's it called, G and G1, then a power of F is in the ideal generated by G and G1. So this is a special case of what we, of course, today call Hilbert's Nullstellensatz, and indeed Hilbert in 1893, just before the report of Brill and Noether came out, although this is not explicitly mentioned there, proved in this paper on invariant systems. So this is one of the things, but I want to mention, before coming to my actual story, one other paper by Noether about space curves, because most of what I'm going to tell you is about space curves. What is a space curve? A space curve is a curve which does not lie in a plane. It lies in higher dimensional space, but usually, and certainly for my talk, this space is three-dimensional space, more precisely three-dimensional projective space. This is what I mean by space curves. So there is this paper about Raumkurven, space curves, by Noether. It dates from 1882, and he won the Steiner Prize for it of the Berlin Academy. So it was very well received. And there are things that you find there which I do not at all have the time to discuss here in detail, but the situation that he's looking at, and this you bear in mind for the follow of my talk, if you have a space curve R like Raumkurve, which is realized as the intersection of two surfaces in free space, and then you take, so it lies in the intersection of two surfaces, but if you look at the whole intersection of the two surfaces, there will also be another curve R prime. So this is the situation that he's looking at, he's studying and combining with co-residual groups of points that were very well known at the time from the study of plane curves. And this is, again, the situation. So you have a curve RPM, or a space curve of degree m, given by an equation of degree m, and of genus p, which goes through a curve f mu. So that's a hypersurface in P3, given by an equation of degree mu. And but the same surface also goes through another curve. So you have different components in the intersection of two surfaces. So this is the sort of residual study that is very much present in many papers of the time, and in particular in the study on space curves. And it goes a long way. I just mentioned this paper by van der Waarden of 1931, where he says, well, you have this residue theorem, and this he only quotes it for curves in a plane, and this is deduced from the fundamental theorem that I have shown you before, the Hauptsatz, but there is a mistake in this, and this paper will be the beginning of a hard time for van der Waarden when he encounters Severi for the first time, is very severely criticized by Severi, and then changes his whole way of writing, the whole way he writes about algebraic geometry. This is a major turning point in van der Waals, and we'll come to that. But let me now start my case study with a quotation by Fleck. What is a fact? A fact is supposed to be distinguished from transient theories as something definite, permanent, independent of any subjective interpretation by the scientists. It is that which the various scientific disciplines aimed at. So the fact that I'm talking about can be seen in Kronecker, for example, in his course again on general elimination theory. He states a theorem, and he proves a theorem in this course. Every system considering of an arbitrary number of polynomial equations in n variables can always be replaced by a system of at most n+1 equations in the same variable. So you can reduce the number of equations you need to determine your algebraic set. And this is a statement which is already in his fundamental work Grundzüge, published in 1882 in Krelle, and the year before for an occasion related to his teacher Kummer. So this raises the question, when you have an algebraic set cut out by a certain number of equations, Kronecker tells you that you can reduce the number of equations always to n+1 if you are in n-dimensional space. But is this optimal? Or can you maybe always reduce it to n, and so on? And so there is, in 1891, still before the report by Brille and Noether, but it's not quoted there, a little paper, which is hardly more than 1 page in Krelle, by somebody called Carl Theodor Vahlen. And so let's look at it paragraph by paragraph. It's so short, we can do this. Paragraph 1 reminds the reader of Kronecker's statement about n+1, and the resulting question, is this optimal or not? And proposing to answer this question. Paragraph number 2. He now looks at two surfaces in 3 space of degree mu and nu, respectively. And you take their intersection, and this intersection has 2 curve components. It has one space curve of degree m and genus p, and another one of degree m prime and genus p prime. Okay? And then he computes, and I will not say anything here because I'll show you on the next slide where this comes from. The little s, small s, is the number of intersection points of these 2 components of the intersection of the 2 surfaces that you cut in space. So here it is. It's a formula. And then he says, so what about if you really want to represent the first of these 2 components, the RMP, as an intersection of surfaces, you need at least one more surface. So take another surface of degree R, of order R, passing through this first one, and then you want to see whether it can eliminate all the points of the other component of the first intersection which are not on this curve. And so this is the capital S, the number of points that are outside of the first component of the intersection, and you just want to count them, and this results from this formula for little s, because the number of all intersections of the surface of degree rho with something of degree m prime by Bezout is this, and then you deduct the points that you already see on the other component, in the intersection of the 2, then you use this formula, and that's what you get. All right? Fine. So that's a computation. And where does the formula for little s come from? Well, it's just quoted from Noether's paper on space curves. It's just there. Everything is in Noether. No problem. You can quote this. The most reliable reference on space curves at the time. And now comes the last section, last paragraph of this little paper by the young student of Kronecker's Vahlen. he does a little computation showing that if you take a specific example, a rational twisted quintic with only 1/4 secant, this is an example that occurs at the end of Noether's paper. So it's a curve of genus 0 and of degree 5, and it's parameter, so it's genus 0, so it's parameterized from P1. And so there are many such curves of genus 0 and degree 5, but there's in particular one that has one line that cuts it in 4 distinct points. And this is discussed already in Noether's paper. This is not contained in any surface of degree 2. So when you want to cut this out in 3 space, this particular rational twisted quintic curve, you cannot use quadric surfaces. It would be the easiest. So you have to have surfaces at least of degree 3, but with 3 doesn't work because this is not contained in such a set. So you have to have, if you want, by what Noether says, and so the last curve that you need to cut it out, if you want to cut it out by 3, would have to be a surface of degree greater than 3, and that just doesn't work because then the formula for capital S gives you extra points. So it doesn't work. Simple computation. So this was a mathematical fact accepted by everybody, printed in the encyclopedia, showing that Kroneker's theorem, that in order to represent in n space an algebraic set by as few equations as possible, the n+1 that Kroneker gave in his theorem is optimal. Here is the example. That's the mathematical fact. Now we make a jump in time, a mathematical controversy. There is after 1933, under the National Socialists in Germany, in 1936 they create a special journal of mathematics inspired by National Socialist ideology called Deutsche Mathematik, and they have memorable quotes in there. And Bieberbach, in one of the first issues, well, in the 1939 issue, quotes Gauss saying there are no real controversies in mathematics. Well, let's see. So in 1941, we are in World War II. We are 50 years after the paper by Fahlen. Somebody from Munich, Oskar Perron, who's not at all in algebraic geometry. He has worked on more analytic things. He has also published a book on algebra. But anyway, publishes a little paper where he just shows that Fahlen's curve can be represented as the intersection of 3 surfaces, which is exactly the opposite of what Fahlen showed. I mean, it's not an example. How does he do it? He does it completely elementary and explicitly. The level is the exercise in a lecture course on linear algebra first year. So, okay, so I don't really, I have to go quickly, but so so you are in projective 3 space, so you have homogeneous coordinates x1, x2, x3, x4. You want to write down the equation of your space curve, which is rational, which has a degree 5, and it admits a line that intersects it in 4 points. So you adopt your projective coordinates xi in such a way that these 4 intersection points are 0, 1, 1, 0, 1, 1, and a 4th one, which is alpha 1 in projective coordinates. You adopt it that such that the secant is given by x1 equal to x2 equal to 0, and then you deduce from that the curve which contains these 4 intersection points, the equation of the curve in terms of these parameters rho and these projective coordinates rho sigma. Okay, and So after adjusting these things with A, B, C, D of determinant 0 that you obtain from as the amount of imprecision of the way you wrote your quadrisecond, you get this as an explicit equation of your curve. And now you just eliminate rho sigma in various ways between these formulas for the 4 projective coordinates. Again, I mean, I assure you this is just an exercise in linear algebra that every student, first-year student, if you explain what you are allowed to do, can do. So this gives you 3 equations. The first 3 are eliminating between the first equations of the xi. And then there is the third equation, which is a 15 by 15 determinant. So you write one line, and then the next 4 lines will be the same line every time shifted to the right. So one set of 5 lines, second set of 5 lines, the third set of 5 lines, each repeated, shifting them to the right. Okay, so here you have 3 equations, and it is, so he takes another page explaining it, but let me assure you, it's completely elementary, clear for everybody. The intersection of these 3 equations, of these 3 surfaces in projective 3 space, is precisely the curve that we want. It's Fahlen's curve. So there are reports by van der Waden, by Weizenböck. Okay, don't say anything about Weizenböck here, it would take me too long. And also in math reviews, very new at the time, it is known that the points and so on. The question is therefore still open now as to whether there exists a curve which is not the complete intersection of 3 or even 2 surfaces. At that time, we are in 1941, somebody like Walker, a student of Zariski's, uses complete intersection not the way that geometrists use it today. It just means taking into account all points. It does not mean that the ideals are the same. Okay, now what happened? So Fahlen's example, which showed that Kroneker's theorem was optimal, you need at least 4 surfaces to cut out this curve, is now proven wrong by what Fahlen says. But what happened? And there's a very strange comment in Fahlen's paper, in Perron's paper about Fahlen. Herr Fahlen, he says, has not computed anything, has not calculated anything in his paper, but he thought he could deduce from enumerations that 3 surfaces could always have to contain other points alien to the curve, fremde Punkte. I have underlined this there. But this is not so. I will rather show below that already the most obvious 3-cone surfaces which one obtains from the parameter representation of the curve by eliminating the parameter do not have any points in common which are alien to the curve. So it's very strange that Fahlen says, that Perron says Fahlen has not computed anything, because after all, there are a few computations that I have shown you in this short paper by Fahlen, but I think what Perron wants to suggest is that he did not do Schubert calculus. He did not do this method of computing intersections that was so popular at the end of the 19th century, but was lacking foundation, as Hilbert pointed out in one of his problems in 1900. So what was this paper about? Why does somebody like Perron suddenly is interested in this question? Well, we have to look at who Fahlen was. If you look in the Deutsche Mathematik, you open it and you see that Fahlen is the main editor of Deutsche Mathematik, of this National Socialist. And there are also certain mottos by Fahlen. For example, in 1939, you read in Deutsche Mathematik, Forschen heißt kämpfen. To do research is to fight. To wrest from the mathematics its deeply entrenched truths requires force, courage, toughness, and it forges the character into steel. So Fahlen actually was the son of a professor in Vienna. He studied mathematics and other science and physics in Berlin. He did his PhD, his doctoral thesis in '93 on additive number theory under the direction of Frobenius and Hermann Amandus Schwarz. He published in 1905 a book on abstract geometry in the spirit of Hilbert's axiomatic style approaching geometry. He published quite a number of articles, and he became in 1911, before World War I, a professor in Greifswald. Then came World War I, and that changed his life dramatically. He was very distinguished as a participant in World War I. He got several special medals for his courage and so on. But during World War I, his work turned to applied mathematics, question of ballistics and things like that, and he never would come back to pure mathematics after that. So World War I changed his outlook on mathematics completely. And then is the time after World War I, when in Germany the Weimar Republic, a democratic regime, is instituted, and he doesn't like that at all. He's very early a member of the National Socialist movement. He becomes Gauleiter of Pommern, so in northeast Germany in 1924, but he is against Hitler at first. He is part of the Strasbourg group within the National Socialist movement. We are in the 20s, so he at first opposes Hitler. And then comes the 11th of August 1924. This is a day of memorial for the foundation of the democratic regime in Germany. And at that time, he is at Greifswald University, and he's not only a professor, he is pro-rector, pro-president of the Greifswald University. And so he orders the Weimar flag, Schwarz-Rot-Gold, to be turned down, and the imperial flag to be dressed at this event at the Greifswald University. And as a consequence of that, and that is one of the rare examples where the democratic regime dismisses somebody from his professorial position for political reasons, he's thrown out. He loses his professorship. He's no longer a civil servant of Germany. He does continue to have a research stipend, which will be discontinued in 1929. And so after that, in 1930, he obtains again what is called a Lehrkanzler, so a professorship in Vienna, in Austria. So then comes 1933, Hitler comes to power, and this old, courageous National Socialist is reinstated in his professorship in Greifswald in a big ceremony and so on. But now he's pretty old already and very distinguished and politically just a wonderful hero for the National Socialists, and so he doesn't really stay in Greifswald. He is in Berlin working for the Ministry of Education. Has a very high position there, and it is also through the ministry that then the journal Deutsche Mathematik will be founded. Now, as for the relationship between Vahlen and Peron was not very well liked, not liked at all, was hated by the National Socialists among the mathematicians, in particular Bieberbach, because he directed the setting of the German Math Society in 1934. And so as a consequence of that, Bieberbach spreads the word about how terrible Peron is politically, and therefore that he has to be removed from his professorship in Munich. And so Vahlen, who is at the ministry, actually sends a letter. You see, this is his signature, Vahlen, with this. He sends a letter from the ministry to Bavaria, to Munich, to remove Peron, but the Bavarians stick with their fellow. Bavaria doesn't like when Prussians, anyway, so Peron keeps his position. So you see, there is a political background, which is of course not spelled out in Peron's paper, but it is there. So what happens after this? So Peron has destroyed this counterexample that Vahlen had published as a student and which he was known for and applauded for, and now the political friends of Vahlen have to somehow defend him. So you have a whole list of things. So this was Perron's paper, and then the immediate answer is, of course, given in the Nazi journal Deutsche Mathematik, right, by somebody called Leithäuser, who has not left any further trace as far as I know. So it's a short paper, and it's one of these rare examples where you have now, and you have several examples here in this debate, where you have mathematical papers that use strategies of argumentation which are exactly like in politics. So Leithäuser picks up the fact that there was the word fremd, fremde Punkte, alien points in Perron's paper. And he says, instead of, whereas Vahlen's goal was to represent this curve purely, a pure representation of a curve as the intersection of surfaces, four surfaces, Perron avoids the word pure, like in purees and so on, and replaces it with fremd, alien. So this is a purely political discussion, and it's like this that Leithäuser answers. Okay, so you may say, well, that's just the political journal Deutsche Mathematik, of course, not surprising that. But there are other mathematicians who join this argument in their texts, so, okay, Perron answers this. Let's pass this. So one of the most important people who joins Leithäuser in his argumentation is nobody less than Francesco Severi. Here you see him in 1937 at the Göttingen bicentennial. So Severi is, of course, a person in algebraic geometry in Italy who spans two different generations and periods in his long and very active life. And I had briefly mentioned that he had convinced van der Waalen to try to make his papers on algebraic geometry more palatable for the Italian readers, which van der Waalen obeys and does. And so he immediately publishes and has it translated into German and published in German in 1943 an answer to Perron's example, saying that, well, it's very nice that somebody like Perron, who has never done algebraic geometry, now occupies himself with these questions, but in fact it's wrong. Turns out he was doing it a little bit too quickly. So first of all, so Perron can show, and he describes this as typical for the lack of rigor in Italian algebraic geometry, that Severi's two proposals that he gives. So Severi in his paper doesn't give one precise definition of intersection multiplicity and how to look at intersections properly, but he gives two, and they're not the same. They contradict each other, and also they have a problem with Bezout's theorem. Well, I mean, this is what happens in Severi. I mean, he never gives one proposal, he gives several ones, and then there are often difficulties with details, but here it's particularly bad for him, I guess. And so as a result, this is a paper, so this paper answering Perron in this political controversy about Vahlen's example is not reproduced in Severi's in the edition of Severi's complete works, complete papers. And instead he replaces it by a little, it's here, viene qui prodotto. Okay, so this is now here the Memorie Scelte. And what he says there is, what he proposes is there is a confusion underlying this problem with Perron's counterexample to Vahlen's example, Perron's counter-argument to Vahlen's example. It is that once we talk about intersection and once we talk about something else, which he wants to call interferenza, not intersezione. So he introduces a new word without defining precisely what this is supposed to be. And he comes back, Severi in a later paper, to the same point in 1948, defending as ever Italian algebraic geometry and its rigor, both against German algebraists and against André Weil. So, fine. This, what I showed you is, even though I had to go very quickly, how this political background of the paper by Perron against Fahlen's example creates a production of papers which are more political than mathematical, even though, of course, they contain mathematical ideas. In fact, Severi could have done better. He could have gone to his bookshelf and pulled out a textbook on algebraic geometry, I mean the last part, the most difficult part of this textbook, Enriquez and Chiesini, 1924, where they discuss qui nasce il problema, essendo data una curva gobba, if you have a space curve C, è possibile condurre per essa tre superfici, so you can try to represent it as an intersection of three curves. So this is the question, and Fahlen ha dato risposta negativa, has given a negative answer to that, and therefore showing that the perfect, and I highlight this, the perfect representation of a space curve needs in general 4 surfaces to get it represented as an intersection. And then comes the commentary of this by Enriquez, and again the essential word is that the intersection has to be perfect, although it is only alluded to what Enriquez wants to say with this, namely that all the points are given with their proper multiplicities on the intersection product, on the curve that you intersect, and so before he says that it cannot be excluded that if you do not limit yourself to perfect intersection, then you quando tre superfici abbiano un'unità ulteriore infinitamente vicina. If you have infinitely near points to certain other points, then it can happen that you can even do it with 3 surfaces. So Enriquez was completely aware, even if he hadn't worked it out in the same elementary fashion, of the possibility that this example of Fahlen is wrong if you misunderstand the way that intersection is understood. So this is a little takeaway from that part of my talk. So Perron interprets the big rewriting of algebraic geometry as a mere conservative reaction against the lack of rigor in the Italian school. Severi, on the other hand, tries to defend the particularly Italian way of doing algebraic geometry. And this has a background story, which is an integral part of the history of algebraic geometry, with André Weil working at the time, with Zariski working in the States, and with, on the other hand, in Europe under fascism, the attempt to create a peculiar mathematical axis between fascist Germany and fascist Italy in the field of, as of 1938, in the field of algebraic geometry, into which the textbook by van der Waden is then integrated. But Perron is not part of these background happenings in algebraic geometry. He's an outsider who has just, for political reasons, stirred this debate. Okay, how does history go on? World War II ends. The Italian and the German fascist system are no longer there. So things look maybe brighter, pastures new, and there is a whole set of papers dealing essentially with what one calls, as of then, as of the second half of the 20th century, the set-theoretic intersection in algebraic geometry, and in particular Martin Kneser, in a marvelous 3-page paper which takes you at least 3 weeks to understand approximately. It's incredibly dense, proves that, 1.5 page, I'm sorry, even less, that every irreducible algebraic curve in projective 3 space is set theoretically the intersection of at most 3 surfaces, and there are lots of other papers and developments on this. Since I'm pressed for time, I go very fast, and I just show you a little quote from a lecture course given by Wolf-Dieter Geyer in Brazil in 1974, where he still shows that he doesn't really know what's going on. This is so interesting here. It took 50 years until Perron remarked in 41 that Vahlen's example fails to be one. The mistake in Vahlen's paper has something to do with not separating clearly the two notions of description, set theoretic and ideal theoretic intersection. It's actually not true, but okay. So still in the 1970s, nobody talked about this political character of the debate at the time, but the mathematics was not completely cleared up, and there's a whole paper, given lots of references and commentaries, that tries to improve this. So now, the last twist, I put under a quotation from the philosopher Wittgenstein. It is a strange error of mathematicians that some of them think that through foundational criticism, this is written at the time of the foundational crisis, late 20s or beginning 30s, something could get lost in mathematics. And Wittgenstein says some mathematicians have the completely correct instinct. What we have calculated once cannot get lost or disappear. So when I was first thinking about this, I somehow got into, because somebody recommended him to me, I got into contact with an algebraic geometer. So this was in the late 90s, I guess, Frank Olaf Schreier, at the time in Saarbrücken. And so I wrote him a mail, didn't get any answers. And 3 weeks later, he answered, yeah, sure, Vahlen was right. And that's it. I mean, so given a curve, space curve of g dis p and degree m, and now comes a little condition that, of course, occurs in none of the texts that I've been alluding to before, which is generically complete intersection of two surfaces. This is not the case of the 3 curves that Perron has in his counterexample. But given such a curve, you write the intersection of as the union of 2 curves. Then the curves, the 2 parts of this intersection in P3 are in liaison. Not dangereuse, but just liaison in the sense of Peskin and Spirot. So this is a theory that dates from 1974. And it is exactly that. You take 2 things, intersect, and they are 2 components, and then these 2 components, in this case space curves, are in liaison. And there's the whole theory scheme done, of course, in the context of Grothendieck's algebraic geometry in the 70s. And this is why I showed you, without explaining the details, because it would have taken infinitely too much time, 2 clippings from the paper on space curves by Noether. This is really a generalization in the new context of algebraic geometry of things that Noether does in his old paper on space curves, where you Restsatz and so on, where you look at the different components that you get when you take one intersection. So they are in liaison. And using this paper, and then you just go through Peskin and Spirot, you get these formulas, and you get exactly, precisely the formula for small s that we have seen in Vahlen's paper. So it's justified in the sense of degree of the intersection. Then you compute the capital S, just as before. It's everything just in Vahlen. The numbers come out correct. We have once a supplementary condition at the beginning. And so by exactly the same argument, you see that 3 surfaces do not suffice. So the conclusion is that Vahlen has shown that now it's the modern terminal, that the ideal sheaf of this twisted quintic cannot be generated by less than 4 equations. And if you look in today's literature, intersection theory, William Fulton, unfortunately, even though he gives so many historical examples, he does not mention Vahlen's example. It's really a pity, but he mentions a very analogous example, and again with reference to the liaison theory by Peskin and Spiro. It's not a rational, it's not a curve of genus 0, but a genus 1 in degree 5 in P3, which cannot be represented by three surfaces. And so in order to really do the history of that, which of course is not my goal today, you would have to look at other prior stages of the Peskin-Spiro theory, but I want to come to an end to have time for discussion. The historian has to do more than to write a report. I'll be free to add as many comments on the translation of Brill and Noether as we would like. This is a question that we will have to face, but let me just end by giving you the final takeaway. You never know what's hiding behind a mathematical text, and sometimes, even though it doesn't happen that often, but I have shown you a particularly memorable example, what's hiding behind it is just politics. Thank you very much.
We have time for some questions. Are there any questions for the speaker? Yes?
Yeah, thanks, Norbert. I had a question back to controversy about this issue about the terms they used, like pure versus alien. And so you said, so this is a political issue mainly. But then after that, in severity, you had the idea of perfect intersection. And you say, just alluded to, it's not, or at least I understood that. So can you explain a little bit more?
Okay, maybe I was...
The issues at stake about this, these words, they oppose one to the other. Is there a meaning that they share and what they mean as pure, alien, perfect? Is it political? What does it mean? Is it political as well in severity?
Lighthizer comment is very short. He does not explain what he means, and Lighthizer comment on Perron's paper is a clear example of a political debate. There is no mathematical explanation at all. He says one should talk about reine Darstellung, a pure representation, and he means something like you have to not just get all the points on the variety that you represent as the intersection of so many other varieties, but you have to get each point. Probably he thinks something like multiplicity, but he doesn't explain that. He doesn't go into detail. He just catches on the fact that in his introduction, Perron had used the word fremd, and so instead of speaking about pure representation, he only cares about alien points, and it's a pure, this is typically what you do in political debates. Yeah? You pick up a word that your opponent has used and you throw it against him. That's all that Lighthizer does. Severi is different, but Severi, being Severi, in his answer, in his immediate answer, the first article to Perron, he does not give one definition of intersection multiplicity, but he gives two different ones. And then it's very easy for Perron to answer that because they are not mathematically equivalent, and one of them has problems with Bézout, so, so it's just a mess, and so it's a very bad attempt to, but he does it too quickly, and so that's another subject. And then perfect was not in Severi, so Severi then tries in his later, at the end of his life, later comment on this paper written too hastily. He proposes interferenza for what we might call set-theoretic intersection, so just getting the points but not with the correct multiplicity, something like that. He says interferenza instead of real intersezione. And then the perfect notion is in Enriquez. And that is, I think he has a relatively clear idea of what he wants to do there, but it is not spelled out. I mean, it's just a short comment, but he, okay, so he is, but the difference between all the other authors is that he already in 1924 sees that in a weak sense you can represent this curve given by Fahlen as an example as the intersection of three surfaces, but it will not be a perfect. And then he never defines what he means by perfect intersection. He just says, well, there will be some infinitely near points, and so it's sort of vague. But he never gives a general theory of what a perfect intersection is. It's just a commentary written like that.
Question. So, was the Italian school aware of Hilbert's Nullstellensatz in the 30s?
Well, they certainly were aware of the fundamental theorem and its various versions, but
then why was there this confusion between set theoretic and scheme theoretic? I mean, because I mean, if you have that theorem, you understand that there's a difference. I mean,
well, how should I answer this? The basic idea is that the Italian algebraic geometers were aware of everything. The way to write it up is another problem. This is sort of, I mean, this is a very way of expressing myself, but I mean, and sort of the standard, I mean, Severi in his later life wrote many articles, especially then also against André Weil and others, and he always says, but we know all this, but the way it's written up is often in a different language, or so this is the big problem of writing the history of algebraic geometry, of which this Noether project is part. So like, look at your question. Your question was, then the difference between set theoretic and ideal theoretic intersection is obvious. But this terminology that you use is a terminology that did not exist before the 1950s. So everybody has his own way of expressing things, and there is not one way to sort of come to a generally accepted neutral formulation of these things. It's essentially a communication problem. But in the particular case of the counterexample that I was showing you, worse things are added to it, as I explained in this controversy.
yeah. Thank you.
Yes?
Yes, I'd like to thank you for a fascinating talk about how mathematical controversy migrates into politics. But I have a very specific question. I was unable to remember from the beginning of your talk, where exactly is it Fahlen admits the criticism put forward by Perron? In other words, where he fails to make explicit the necessary condition on liaison. Could you go back and point that out?
Fahlen never answers Perron. He has other people who do this. So Perron is 1941. Fahlen was very young when he did this, 1891, 50 years earlier. So Fahlen just wrote this paper when he was young. Later on, he did other things. But now, in 1941, he is, by the way, since 1938, he is president of the Berlin Academy. So somebody has to defend him. So Leithäuser comes in, Severi comes in, and so on. I'm afraid I don't quite understand the question.
Well, in the early paper from the 1890s, there must be a point at which, if in order to reconstruct the paper, one would mention the correct liaison between the structures that come together.
Oh, I thought I did this. I see.
Oh,
I mean, this was the, sorry. Okay, I should show it to you. This was the this is the modern way of Fahlen. Every single step in Fahlen is followed. The computation of little s, which Fahlen just quoted from the space curve paper by Noether, and then the capital S, exactly as it is calculated in Fahlen's paper. So the formulas are justified. In this scheme theoretic, this is very modern, and quoting, I mean, using Peskin and Spiro, the theory of liaison. So, but these formulas are precisely the formulas that Phalen has, and it is only these formulas that he needs to show that you cannot represent this in a way matching these formulas as the intersection of just three curves. So that's why Frank Olaf Schreier, when he finally answered my mail after 3 weeks, he said, well, Phalen is right, except that you have to justify the things differently today.
Yeah, so thank you for the presentation. So my question was, the question is, when politics mix with science, some things go wrong. And I feel so, because now we have seen that at some point, someone lost his job, lost so many things. And I was wondering what the mathematical society were doing at that point, just in relation to his question, when he said, was talking about the Italian schools, if they really want to. So what was like a way of helping out in this situation?
You want a recipe? Well, I mean, politics is always there. And we are in scientific institutions, and there is a certain background which is necessarily political. But it is, in mathematics, relatively rare to see mathematical papers about a mathematical fact or claim, proof, which in the way that they speak are purely political. And this was what when I first saw this, attracted my attention to this particular case study. But that politics is, you mentioned that the last book I published was Framing Global Mathematics, sort of the history of international organizations in mathematics in the last 2 centuries, and certain main things of this. There, of course, you have an interaction of politics and mathematics in various contexts and over the last 2 centuries explained. But here, it goes deeper into the mathematical debate of one particular example. And I did not develop this, but I alluded to this, for example, with this plan of Hasse and Severi to create a German-Italian axis in publishing about algebraic geometry, which dates from 1938, where you have not the mathematical content, but concrete action in favor of publication series and so on, which was explicitly the axis in mathematics, which was explicitly motivated by the political situation. So you have occasions like that every once in a while.
I think we're going to have to call the questions to a close and thank the speaker once again.